So SpaceX just pulled off the single biggest IPO in human history. They raised a staggering $85 billion. But what's truly fascinating here isn't just that massive pile of money. It's the product they are betting all of that capital on. It's a brand new satellite called AI-1. Welcome to this explainer. Today we're going to unpack what honestly might be the most ambitious industrial product ever designed. We'll look at how it promises to completely solve the biggest physical bottlenecks in artificial intelligence today, literally by moving computation straight into orbit.
Okay, let's dive into this, because to really understand AI-1, you have to realize that this is definitely not your normal everyday satellite. A typical communication satellite, it runs on maybe 10 to 20 kilowatts of power. But AI-1 is designed to hit an absolutely astronomical 150 kilowatts of peak compute. What SpaceX is fundamentally doing here is taking an entire NVIDIA GB300 liquid-cooled cabinet, we're talking 72 extremely expensive, incredibly power-hungry GPUs bolted together, and dropping that exact massive compute setup right into space.
And to feed a single box of chips that much power up in orbit, you need a machine of just absurd scale just to gather the sunlight. 70 meters. When it's fully deployed, this satellite is literally wider than a Boeing 747 commercial airliner, and it stands about 20 meters tall. It's essentially this colossal structure made almost entirely of solar panels, just unfolding out there in a vacuum, existing solely to act as a floating power plant for one single rack of AI chips. It is mind-blowing.
Section 1. Earth's compute bottleneck. Running out of power and cooling.
Now, you might be wondering, why go through all this immense trouble and expense to launch a satellite this big? Well, it's because right down here on Earth, AI is hitting a massive physical wall. Modern AI data centers are absolute monsters when it comes to electricity. A single AI campus can pull anywhere between 100 and 300 megawatts. Just to put that into perspective, that is enough electricity to power a small city, all contained within one single building. And we're already seeing our physical grids buckle under the pressure. Take PJM, right? They're the largest electricity grid operator in the US, managing power for about 65 million people. Well, in a recent capacity auction, they came up roughly 6.5 gigawatts short of the reliability target. It's literally the first time they've ever missed it. Data centers are quite literally eating up demand faster than we can build new power plants. If you want to plug a new AI campus into the grid today, you're looking at a years-long interconnection queue just to get permission to draw power.
But here's the thing. Generating power is actually only half of the terrestrial bottleneck. It goes like this. Step 1, chips make heat. Step 2, fans blow air. Step 3, data centers basically become giant cooling systems. Think about your laptop fan for a second. It spins up because those chips turn electricity into heat, and if you don't aggressively remove that heat, the chip literally cooks itself and dies. On Earth, we use massive amounts of air and water to cool these giant warehouses. An AI data center is, in reality, just a building-sized cooling system with computers tucked inside. Getting rid of heat is absolutely our ultimate earthly bottleneck.
Section 2. Solving power in orbit. Uninterrupted solar energy.
So up there, in the right orbit, the sun never sets on your solar panels. There are no electricity grids, no water bills, no neighbors complaining about the noise, and crucially, absolutely no multi-year interconnection queues. It's just raw, uninterrupted solar energy floating in a vacuum, which, perfectly solves the power generation bottleneck. But that vacuum introduces the single hardest engineering challenge of this entire project. How do you cool a chip with no air? Down here on Earth, we rely on convection. We blow air or we run water over hot things. But in the vacuum of space, convection is physically impossible because there's literally nothing to touch. The only way to get rid of heat is to radiate it away as infrared light. The heat literally has to leave your machine as light. And while space might feel like a cold place, it doesn't actively cool things down for you.
Let's do some quick napkin math to see why this is such a severe problem. AI-1 is packing 110 square meters of deployable liquid radiators. If you run those radiators at room temperature, so about 20 degrees Celsius, they shed roughly 70 kilowatts of heat. But remember, the average compute payload of this machine produces 120 kilowatts of heat. So if they run it like a normal system on Earth, the math completely fails. The thermal system gets overwhelmed and the satellite just cooks itself to death.
Now, what's really interesting about this slide is the physics cheat code that saves this entire orbital cooling project. It's called the Stefan-Boltzmann law. Basically, this law states that radiated heat doesn't scale in a straight linear line with temperature. It actually scales with absolute temperature to the fourth power. And this right here is the absolute secret to making orbital compute actually function without needing a single drop of Earth's air or water.
Because of this law, if you just double the absolute temperature of your radiator, you don't just get twice the heat dumped. No, you get 16 times the heat rejected. So SpaceX doesn't run their liquid cooling loops at room temperature, they actually run them dangerously hot, pushing them up to 50, 60, or even 80 degrees Celsius. By doing this, heat rejection multiplies exponentially. The liquid coolant pulls the heat off the chips, carries it over to these scorching hot radiators, and beams it away into the void as infrared light. Boom, completely solving the cooling bottleneck.
Section 3. The economic reality, making space compute viable.
Okay, so the physics works, but what about the economics? Because right now, putting compute in orbit is incredibly expensive. We're looking at upfront capital sitting around $51 per watt in orbit, compared to about $16 per watt down here on Earth. That means orbital compute currently costs nearly 8 times more than building that exact same capacity on the ground. And the hardest reality of all that upfront cost, it's the AI chip lifecycle. Look at this brutal timeline. You launch a state-of-the-art chip at year 0. By year 1, a dramatically better generation of silicon has shipped on Earth, completely making your orbital chip obsolete. And by year 2, it's essentially just dead mass floating 500 kilometers above our heads. You can't exactly just send a technician up there to swap out a GPU, right? So to stay competitive, you have to constantly, relentlessly replace these massive satellites.
And this is exactly why SpaceX is just throwing away the old satellite rulebook. For 60 years, old space meant hand-built, highly precise, radiation-hardened satellite jewels that were designed to last 15 years purely because a single launch was just so rare and expensive. But new space, with AI-1, it means mass-produced, disposable, and cheap. They are building AI-1 the same way Toyota builds cars or Apple builds phones, literally by the millions on a massive assembly line at a 1,000-acre gigasat plant in Texas. Because when mass is cheap, you stop trying to make perfect handcrafted jewels and you just start making disposable, replaceable hardware.
Of course, a lot of people think this is a terrible idea. There is deep skepticism from Wall Street and tech analysts, which has led research firms to call this whole idea peak insanity and AI snake oil. One really respected Wall Street analyst shop, Morningstar, gives this moonshot scenario a mere 7% chance of actually working out. And, it's a completely valid concern. It suggests that a huge chunk of that $85 billion IPO valuation is tied to a space story that might just turn out to be hot air.
But those skeptics might be missing one massive piece of the puzzle here. The demand is already here. SpaceX is already leasing compute to the biggest AI labs in the world down on the ground. Google has committed $920 million a month for AI compute. Anthropic committed $1.25 billion a month. That is tens of billions of dollars in guaranteed revenue. These companies are in an all-out race to build the smartest AI on Earth, and they desperately, desperately need power. AI-1 is simply taking this exact, highly profitable, and proven business model and lifting it straight into orbit.
And this brilliantly illustrates the final piece that makes these economics possible: launch costs. Right now, launch costs hover around $1,500 per kilogram, but SpaceX's massive, fully reusable Starship is designed to crush that cost down to a target of roughly $185 a kilo, maybe even lower. When you can launch massive amounts of hardware into space that cheaply, constantly replacing obsolete, disposable AI satellites suddenly goes from an economic nightmare to a highly viable, scalable operation.
If they pull this off, intelligence literally moves off-planet. By taking computation to space, SpaceX so elegantly removes the physical power and cooling bottlenecks that are entirely strangling Earth's data centers today. The sun provides unlimited, grid-free power. The vacuum of space handles the cooling through massive infrared radiation. And our earthly grids, they are finally spared from collapse.
For the entire history of computing, every single calculation has been trapped on this one rock. So will the future of human intelligence live entirely in the sky? It's a really profound thought. As the demand for AI grows infinitely beyond what our terrestrial power grids and water supplies can physically handle, moving computation to orbit might not just be an $85 billion moonshot. It might be our inevitable reality. Thanks so much for joining me on this explainer, and I'll leave you to ponder just how soon the stars might start doing our thinking for us.